Alright, so guys, hey, Moses here. So looking at today's lesson, it's not a particularly difficult lesson, although again, we have moved past the concept of geometry, where you just do geometry because you did exactly what Mr. Thomas did on the board and we're happy. But now we're moving to the part where you have to start thinking about what you're doing. Looking at all the pieces of evidence that you're given, try to draw conclusions based on those evidences, and having to think your way through the problem. So for a lot of students, the second half of geometry tends to be a little more difficult because of that. But it's really, in terms of skill-based, not a difficult concept, but it's a little more difficult because you have to think outside the box. So we look at things today when we're looking at surface area of prisms and cylinders. There's a reason why we group them together. And then there's this key term between lateral versus surface area. And that's what I want to focus on first. We're talking about lateral versus surface. What does surface area mean?
The area of the surface.
Area of the surface. What does that mean, Keanu?
Oh, I don't know. I know that's what surface area is.
Okay.
I don't use it a lot.
Let's try something here. What would be the surface area of this?
The outside.
So, Bailey. All the sides, and then top and bottom. Basically, that's what we call the total surface area. It's top and bottom and all the sides. That's surface area. But then there's this other weird term called lateral area. For those of you guys who like football, you'll probably understand this a little bit better. Lateral, when we think about a lateral pass, how are you passing the ball with a lateral pass? Technically, it does have to be backwards. No, it does have to be forward. You can have forward progress with the pass. Okay? But in either case, it's not like forward down the field, it's forward off to the side, right? So our lateral area is just the area of the sides. So if I'm looking at this box, it's the area of my four sides. So when they ask you, you're going to really pay very close attention to those details. Are you asked to find the lateral area? Or are you asked to find the entire surface area? So we look at this, the formulas aren't that bad. They're pretty self-explanatory. But there's some small details that's worth going over. And what I want to do first is I want to talk about something called a net. And when we look at things from a geometric point of view, what we're able to do is basically have these nets. And all a net is basically kind of like a network. And what we're going to do with a net is you're going to take a 3D image. In this case, we call this a trapezoidal prism. We're going to take this prism, and we're going to take it from a 3D point of view and turn it into a two-dimensional point of view. And that's all that a net is. It's basically unfolding the shape. When you guys order pizza, it comes in this nice little box, right? But have you ever gone to pick up the pizza and you see the stack of boxes off to the side? They're flat. Okay, that flat representation is the net. And then after you fold it all up, we have the 3D image. So that's really all the net is, the 2D representation of a three-dimensional object. Now, when we look at this, what are all the shapes that make up this prism? Take a look at that. What are all the shapes that make up that prism?
4 rectangles and 2 trapezoids.
4 rectangles. We have 4 rectangles. And we have 2 trapezoids. Now the trapezoids are called your bases. Now notice that the prism isn't necessarily sitting on those trapezoids, but that's what we call the bases of the trapezoid, or the prism. So anytime we're talking about the base of a prism, it's the 2 shapes at the top or bottom or at the ends of the prism. Now, collectively we refer to all these three-dimensional objects as polyhedra. And that's really all it is. When we think about polyhedra, it's just all these three-dimensional shapes put together. So pyramids, cones, prisms, we have cylinders, we have spheres. These are all types of polyhedra. That's why sometimes you'll hear an icosahedron. It's just a three-dimensional shape, right? Like the similar to the house that sits out on County Road 19. Basically, it's a geodesic dome. That's a polyhedron. It's made up of all these shapes that are put together. So when we look at this, it's kind of cool because there's a specific relationship between the faces, the edges, and the number of vertices. How many faces do we have to this prism?
6.
Okay, so we just have 6. Sam, how did you know what faces were?
Like the sides.
Yeah, it's basically the number of sides of the prism. Now, where do faces intersect at? What type of geometric figure is created when two faces intersect? Chris?
An edge.
An edge, yes, the line. So count up the number of edges that we have. Chris?
12.
12?
Wait, how do I
That was 8.
Yes, 12.
Or 6.
Yeah, it is 12.
Well, 12.
So there's 12 edges. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 edges.
Twice as many.
How many vertices are there? Chris?
8.
8.
Huh. No, I find it interesting.
Oh.
You go to 6, 8, 12.
It goes 6, 12, 8.
Yeah, but you put the vertex before the edge.
So what's the relationship here? It's hard to tell with the 6, the 12, and the 8. But there is a specific relationship. What I'm going to do is I'm going to pause this real quick. And what I want you guys to do is very quickly on whatever mobile device you have, find it very fast. I want you guys to look up Euler's formula.
I think this is a trap.
What?
Alright, so in the search, Cheyenne, what'd you find? So F plus V is equal to E plus 2. Yep, but if we bring it all over to the other side. So F plus V is equal to E plus 2. Hey guys, this will work for any shape. For any polyhedra, this is true. The number of faces plus the number of vertices is always 2 more than the number of edges. And so it's a kind of interesting relationship worth knowing. F plus V is equal to E plus 2.
Mine says F plus V minus E equals 2.
Okay, now let's talk about that one for a minute there. F plus V minus E equals 2. Are these the same?
Yeah.
Yep. Chris?
Is the number of edges always going to be twice the size of the number of faces?
No.
Why did I put 5?
It does typically in a prism, but we have a pyramid. Alright, let's move forward.